Have you ever stopped to think about the literal heartbeat of the modern world? Seriously, every time you hear a car drive by, a truck rumble down the highway, or even just a lawnmower clearing a yard, you are listening to a breathing, beating machine. For over a century, the internal combustion engine has powered our lives, taking chemical energy and magically, well, scientifically, transforming it into the mechanical motion that drives our civilization. Today, we're opening up the hood in this explainer to look at the fascinating physics and engineering that actually make all of this possible. So, the fundamental question we've got to ask is, how exactly do we harness tiny, violent explosions to smoothly power the world? Think about it. We have to convert chemical energy from fuel into thermal energy, and then somehow turn that intense heat and pressure into mechanical, rotating motion. And the best part? We're going to make sense of this entire process today without getting bogged down in complex calculus or, those terrifying thermodynamic equations. To keep things nice and clear, we're going to follow a simple roadmap. 1. The anatomy of an engine. 2. The four-stroke rhythm. 3. Spark versus compression ignition. 4. The modern dual cycle. And 5. Real-world power boosts. Okay, let's jump right into section 1, the anatomy of an engine, the fundamental building blocks of power. Right, so before we can understand how the engine actually breathes, we need to know the basic physical parts of our mechanical heart. Inside the engine cylinder, there's a piston that moves up and down. Top dead center, or TDC, is the absolute peak of that movement. It's literally the top of the piston's breath, right before it stops completely and gets pushed back down. You can think of it as the ultimate maximum squeeze point. Now, when the piston reaches that absolute peak at top dead center, there's still a tiny bit of empty space left at the very top of the cylinder. We call this the clearance volume. And what's really fascinating here is that this tiny clearance volume is where all the explosive magic actually happens. All the air and fuel get trapped and squeezed into this incredibly small pocket just waiting to be ignited. To measure the overall size of the engine, engineers use two simple terms: bore and stroke. The bore is simply the diameter of the cylinder itself. The stroke is the total distance the piston travels from its absolute lowest point all the way up to top dead center. Think of the bore as how wide the engine's lungs are, and the stroke as how deeply it breathes in and out. Together, these determine the engine's displacement, which is a massive factor in how much power it can ultimately produce. Moving right along to section 2, the four-stroke rhythm, the breathing cycle of the ideal auto engine. Now that we've got our parts identified, let's establish the rhythm. This cycle, which was perfected by Nicholas Otto way back in 1876, acts as the engine's heartbeat. It takes 4 distinct strokes of the piston to complete one single cycle. First up is intake. The piston moves down, inhaling a mixture of air and fuel. Second is compression. The intake valve closes, the piston moves up, and it squeezes that mixture tightly into the clearance volume. Third is power. A spark ignites the mixture, causing a massive expansion of hot gas that violently forces the piston back down. And finally, the exhaust stroke. The exhaust valve opens, and the piston moves up one last time to exhale the spent gases. Then it's ready to start the whole loop over again. Thermodynamic textbooks are absolutely filled with dense formulas analyzing this cycle. But honestly, the key takeaway is wonderfully simple. As the compression ratio goes up, the thermal efficiency goes up. Meaning, the harder you squeeze that air and fuel mixture before introducing the spark, the more efficient and powerful the resulting explosion will be. It basically boils down to this: squeeze it tighter, get more power out of the exact same amount of fuel. Which brings us to section 3, spark versus compression ignition, the great thermodynamic showdown. So, there is a physical limit to how hard you can squeeze gasoline before it explodes entirely on its own. And this introduces the historic rivalry between the Otto cycle we just talked about and the diesel cycle, perfected by Rudolf Diesel. The Otto cycle, which uses gasoline, needs an electric spark plug to ignite the fuel in a closed, constant volume. But the diesel cycle, it does something entirely different. It only compresses pure air. It squeezes that air so incredibly hard that the air becomes superheated. Then, fuel is injected directly into that scorching hot, highly pressurized air, causing the fuel to self-ignite almost instantly at a constant pressure, absolutely no spark plug required. When we look at the actual numbers behind that squeeze, the difference is just staggering. Because gasoline engines compress a pretty volatile mixture of air and fuel, they can only really handle a compression ratio of about 8 to 11 before the fuel knocks or, prematurely explodes. But because diesel engines are only compressing air, they can push the compression ratio all the way up to anywhere between 12 and 24. That extreme compression is exactly why a diesel engine is so incredibly efficient and doesn't even need a spark. The sheer pressure does all the heavy lifting of ignition. When we weigh the real-world trade-offs between these two amazing feats of engineering, a very clear picture emerges. Spark ignition engines draw in an air-fuel mixture, use a spark, and generally run at much higher speeds with a lighter build, which is perfect for, say, a sports car. On the flip side, compression ignition, or diesel engines, draw in only air, use extreme pressure for ignition, and require a much heavier, sturdier physical construction just to contain those massive internal pressures. Because of that heavy build, they run at lower RPMs, but man, they deliver incredible torque and much higher thermal efficiency. Let's transition into Section 4, the modern dual cycle, adapting ideal thermodynamic cycles to reality. The original pure diesel cycle was fantastic for slow, massive engines, but engineers really wanted to put these highly efficient engines into faster vehicles. To make high-speed diesel engines a reality, they had to create a bit of a hybrid compromise. In a modern compression ignition engine, treating the combustion as strictly constant pressure just isn't entirely accurate anymore. Instead, the heat addition is modeled as partly happening at a constant volume, just like the Otto cycle, and partly at a constant pressure, like the diesel cycle. This clever blend is what we call the dual cycle. Now, how do they actually achieve this dual cycle? Well, instead of waiting until the piston is exactly at top dead center to inject the fuel, modern high-speed engines start spraying the fuel in at about 20 degrees before the piston reaches the absolute top. This gives that first little bit of fuel enough time to ignite and burn while the piston is still finishing its upward travel, perfectly simulating a constant volume Otto-like explosion. Then, as the rest of the fuel finishes injecting, it burns as the piston starts moving down, keeping the pressure nice and high into the expansion stroke. It's a beautifully timed dance that maximizes power output and efficiency. And that brings us to our final part, Section 5, Real-World Power Boosts, Turbochargers, and Historical Quirks. Remember earlier when we said that engine power is largely dictated by how much air it can breathe in? Well, engineers, being engineers, invented ways to force-feed the engine air. A supercharger uses a mechanical compressor driven directly by the engine's rotating crankshaft. It's super fast, but it adds what's called a parasitic load, meaning it actually steals a little engine power to make a lot of engine power. But a turbocharger? That's an elegant piece of engineering right there. A turbocharger uses a turbine driven purely by the rushing exhaust gases leaving the engine. It literally recycles the wasted exhaust energy that was just going to be blown out the tailpipe anyway, using it to compress incoming air and force it into the cylinders for a massive, efficient power boost. And history provides some truly wild anomalies that show just how creative engine design can get. Back in World War I, the famous Sopwith Camel aircraft, yes, the exact one Snoopy flies in the Peanuts comic strips, used a radial engine that turned conventional design completely inside out. Get this. Instead of the engine block sitting still while the crankshaft spun the propeller, the crankshaft was bolted rigidly to the airplane. The entire massive, heavy cylinder block of the engine rapidly rotated in circles around the stationary shaft, taking the propeller with it. This crazy setup kept the engine cool in the air and generated massive gyroscopic forces that allowed the aircraft to perform incredibly sharp, unique dogfighting maneuvers that standard planes simply couldn't match. So, from the Otto cycle's perfect four-stroke rhythm to the extreme pressures of the modern dual cycle, and even those spinning engines of early flight, we've spent well over a century mastering the art of the internal combustion engine. But here's the thing. While we have spent 100 years perfecting the art of harnessing tiny explosions, we're now brushing up against the absolute physical limits of thermodynamic efficiency. As we look to the future with new fuels and new technologies constantly on the horizon, we really have to wonder, what will the heartbeat of tomorrow's machines look like? Are we just going to see a refined combustion cycle, or is it going to be something entirely new? Thanks for joining me on this deep dive in today's Explainer. Keep learning and keep asking those big questions.